I hope I have connected to the right. Oh, okay. Yes.
Hello, Professor.
Okay. Hello, Sarah. Hello, Lina. Oh, Lina is not yet.
Lina is here.
Hello, Lina.
Hi.
Check who else is here. And hello, Boston, and hello, Steven.
Hi.
So I'll make everyone co-host in case you need to share. Yes. Yes. Very good. So just checking. Oh, okay. Here is the board. So the plan for today is multifold. And thank you all for investing your time into the homework, which I admit is quite challenging. So I'll probably deliver the new material, and then if needed, I'll browse through directories if needed and help with your previous homework, because the next one will be based on the one that you completed. So even those who performed really well, there are some options for improvement that will be comments. So the plan is basic states, orbitals, and I have forgotten to email you before, so it will be a little slower, but we all need to install specific new software on our computers. It is free, it is not commercial. New software, which the name is BMD. So in fact, this BMD helps to do orbitals in a really nice way, but I'll show how to do it without, so that we do things really quick. And then I'll demonstrate how to use BMD and maybe how to install it. I have slides from previous years' labs, and I can briefly show them, but I do not believe they're very helpful. It's very basic things that goes much better through regular demonstration. So here are the subjects that we are going to present in about 2 weeks after the break. So next week is a break, and then there will be 2 additional weeks. First week nothing, second week presentation. So we will have about 4 labs on a VASP before you present. Previous one, this one, and then 2 more. And by now we kind of covered the first one, and part of the second question, and the rest needs to be covered. So do you remember from the oh yeah, I can make notes from the last lecture last night? I remember it probably was a little, it was not the most complicated, but it was a little away from comfort zone because it had some physics, right? You remember? So the material that we covered in the lecture last night is one of the most important questions of this month, and we will cover maybe first week after the break. So this will allow all of us to predict optical properties of materials. And if I would be in the class, I would select this one to present. And I'm just giving a little heads up ahead of time. So the molecular dynamics will be main tool for the project. Of course, there will be freedom, and you can select different software. For example, you can do projects with Gaussian. You can practice transition state search if you need reactions, but the ab initio molecular dynamics is most powerful and specific tool that is provided through WASP software. So we will do it just a couple of days before presentations, like in second week after the break. On Wednesday we will cover this material, and on Friday we'll do presentations. So maybe after the break we will make a session where practice democracy, where you select what you want to present. These two anions, cations, and singlets and doublets are quite easy. It will be same thing we already covered for Gaussian, and there will be just specific notations to compute them in WASP. And I believe Boston really wants to present this one, right? You were asking questions about the subject starting from the first day in class. Okay, and today we will cover orbitals, and I do not see density of states here, but it's my failure. It should be somewhere. I will add it. Density of states is not complicated, but it is a critical part that we always do. So you already saw the slides, and I thank you for submitting homeworks. I think everyone got this idea, and there could be some little adjustments. And everyone will be absolutely perfect. So by today we have two goals. Goal number one is to get a picture like this. Yes. And the difference from the density of state that we were doing in Gaussian, that here, well, it is not a big difference, but for interpretation, it's kind of useful. So here, occupied orbitals are highlighted with color, and virtual are kind of
unoccupied.
Virtual or unoccupied. The HOMO, this will be HOMO. Right? So yeah. I'll just show steps, and each of us will do these figures. And the task number 2 is to make figures like this, to plot charge density, orbitals, and visualize WASP output. So for this stuff, when there is a way to draw orbitals from WASP in Gauss view, and we have all tools for this. we'll do it without immediately. But the best quality of images comes out from VMD software, and I believe anyone from the group of Professor Wenji Shah has been encouraged to install this software, right? So you already know, and you can assist the rest of us, or to go it and you will instruct how to get it. There is one more subject that I'm not confident we will be able to cover, but let me quickly draw it on the option and watch what is in the chat line. Oh, thank you for making votes. So number 1, number 2, number 3, and number 4 is I really want to cover it, but I have doubts in my strengths to show it. The by now we were doing all calculations on photon, right? And it is a great facility. Thank you to Steven for keeping it up and running and not excluding anyone from the class from using it. But it is just a little desktop station with just a little extended facilities. We cannot do world competitive research on it. We need some high performance clusters. Everyone is welcome to log into HCCast and do VASP there, but I will encourage use of other facility, so-called NERSC, which is National Energy Research Supercomputer Facilities located in Berkeley. And if time allows, I'll show how to log into NERSC and how to transfer files, of course, and web files, and as well how to launch VASP on NERSC. So for today's program, we can survive without it, and but after you present VASP skills and you'll start working on projects, nothing competitive can be done on photon. So it is not urgent. So we can do it on the next web, but as we go, we should learn it, and when it will be time for projects, I encourage you to run jobs there. And the format and processing of files will be absolutely the same. It's not a big deal. Okay. Focused. Screen. Okay, so maybe I'll start with orbitals. Here is the HOMO orbital of this periodic titanium dioxide nanowire that you were doing last time. Do you recognize it? And the orbitals computed in VASP do not have positive and negative. They have, but VASP format doesn't show which of them are positive, which are negative. And as you remember, for highest occupied, they're localized on oxygens, right? Make sense? you see that it is arranged a little bit more, how to say, symmetric. So they are basically homogeneously distributed over all oxygens, and there will be progression of orbitals, same as in Gaussian, like HOMO, LUMO, HOMO -1, LUMO +1. So I'm going to maybe close this window and do it from scratch. And as I go through, please stop me, because I can get excited with this stuff, considering it is cool, and stop responding to external requests. So please do not hesitate to stop me. So this image is a goal, and here I am in. Oh, and please do not forget to log into Photon through MobaXterm and go into your directory. So when I was here last time, here is the directory where it was, and here are the files that were created, right? So we did create the input files postcar, and then copied the Incar and K points and recreated podcar. And all files with a creation date after this. So this amount of files, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, they are output files of WASP. So in your successfully completed homework, you are looking for the outcar file, which is an analog of the .log file in Gaussian. So you are extracting energies of ionization, affinity, and homolomography. There is file named wavecar, and from the name, it may sound that it is contains wave functions. So the wavecar, in some sense, is correlating to the .chk file in Gaussian, and similar to way how we process Gaussian. In order to plot orbitals, we need special command to extract orbitals out of the wavecar file. Okay, so I'm going to demonstrate these steps, but they all will be in a command line, and just prepare for a sequence of like typing commands. Maybe let me know if I need. Oh, I can copy paste into the chat line, right? If I do something. Okay. Whew. So please let me know if there are any quick questions before we go into practical things. Are there any criticisms, suggestions, general questions, or you permit me to go forward? Yeah, yes or no? Okay. Yeah. Thank you. Thank you. So to avoid confusion with any additional calculations, I'm creating new directory, LAB8, for example. Then I'm going to copy several files from my successful launch of the WASP. So I copy the K points. I copy the car. Note that I do not copy Incar. and I do not copy postcard. I'm copying so-called Concar. If you see here, the Concar, if you look inside, it has the same format as postcard. And for our present run, it will be absolutely identical to the postcard. But as soon as we start geometry optimization, the Concar will contain the result of optimized geometry. So I'm copying the Concar into LAB8, and there I will rename it as a postcard. And in addition, I want to copy the file wavecar into this new directory. So let me copy, but if you will be trying to implement these commands, please try to copy files from your directories, right? And do not create another LAB8B in my subdirectory. Okay, yeah, so chat line to everyone, paste. Okay, now I am going to this new directory, cd LAB8B. No, not B, A. Okay. I have this 4 files, and now let me copy maybe the outcar as well, and I'll explain why. So I'll copy the old copy into here. I will need it just for information. Now I'm going to copy a template file, template binary Incar, it is a directory, and then if I hit the tab button, you see there are like a couple of dozen templates of the Incar. So because I'm lazy, I do not want to retype these Incars again and again, and there are templates for most life scenarios that I may need. And the one that I need now is Incar PC, not for personal computer, but for our charge, which is the same as Orbitals. So let me copy this P. Check. Okay. Okay. So I'll tell a few words before we go into details, because I have a fear that you could be discouraged or lose steam and interest. So when we were practicing Gaussian, there was a command CubeGen, right? That was converting the dot form check dot .chk into orbitals, into cube files. When practicing this CubeGen command, we were identifying which orbital we need to process. Do you remember? I see a question in the face of Steven. No? You are fine with previous effort about CubeGen, right? Okay. And so now for VASP, the CubeGen will be replaced by another command. And for your surprise, the cube_gen, instead of cube_gen for Gaussian, VASP will serve as cube_gen for itself. So one needs to rerun VASP command just with a specific Incar. Please give me a sign if this idea is okay or you want me to develop it better. Okay? Or not okay? Good. So we will need to rerun VASP in this directory. But,
Dr. Kellen?
Yes?
So first, the point of the cube_gen, it's not really clear. And another thing, do I need to use the same file from your directory or copy the files from your directory or what?
I've got your questions. Thank you, and I'm going to address them.
Okay.
I'm just thinking and slower than most of you and speaking even slower than thinking. So, one of the practical aspects that we covered in our previous month was plotting orbitals in Gaussian. And I think Kea did instruct us how to make molecular orbitals from Gauss view without command line. But in class, we were considering how to do orbitals in the command line with cube_gen. Lina, is it okay? Just show okay or not. Okay. Now, the idea is that before we can plot something, we need to convert file formats. We need to prepare the file that we can plot. We need to prepare a cube file. And this cube file is obtained by converting some machine-specific internal information about electronic structure, about orbitals, into some distribution in space that we can plot. Make sense? Okay. Now, for VASP, we had a cube_gen command. For VASP, for Gaussian, it was cube_gen. For like actual electronic structure command was G09, and the command to create orbitals was cube_gen. For VASP, the actual command to run electronic structure is VASP, and actual command to generate orbitals is also VASP. But the difference that one needs to tweak the Incar, the input file. Lina, does it make sense? Okay, good. And what was the second question?
I was just trying to copy the files from your from my.
Okay. Yeah, thank you. I've got it. So I don't mind if you copy from my directory, but just think ahead of your projects when everyone will have individual projects. You will not be able to copy from each other. And for this reason, it could make sense to use your files from your previous attempt, even if you are not 100% sure if they're correct. So do whatever is comfortable for you. I'm not insisting and not forbidding. Please use my files if you need it. But on your place, I would use titanium dioxide nanowires data from your own calculation on the previous lab. And if you were not on the lab, then yes, please copy it from my directory. Yes. Make sense? Okay, good. Whew. And we will speed up. I'm talking too much, but it will go quicker. So now, oh no, I need to speak more. The actual practical part will be quite quick. I just want that we understand what we are doing. We are going to modify Incar file, and after I open it, the one that has been copied from the template, it will look no way similar to what we used in the previous run. Command will be very different, and I will point your attention on a specific keys. It's relatively, it's mid-sized file, maybe 20 lines, in specific keys, specific numbers that we need to change. So which numbers are we going to change? there will be three parameters in this template. First, total number of orbitals for this model. And if you were looking into the, in your homework, you were looking inside the outcar file, right? You are identifying only HOMO and LUMO orbitals, but by doing this, you are seeing the whole list of orbitals, and they are counted, right? So one needs total number of orbitals for specific system, for the system. So it will be first input parameter. Another two input parameters is the range of the initial and final energies, the range of energies for which we want to plot the to find orbitals, or later on to find density of state. So the command will generate the specifics of the command that it will generate not one orbital, but it will create all orbitals in a range from this energy and that energy. And if I know that for this system, HOMO is like -7 and LUMO is -4, I can select maybe from -8 to -2, the range of energies, approximately. So three numbers: the total number of orbitals, or WASP calls them bands, and then the initial energy, minimal energy, minimal, and somewhere final energy for the range of orbitals. Okay, now after this long introduction, we go to the practical side. If I look inside the Incar file, there is a command n-band. So since WASP was written by physicists, they like to call orbitals bands. But we can forgive them this. And if you look further through this file, you'll see the command energy interval. So the command energy interval does have two numbers. So these two numbers should be changed to whatever we selected as initial energy of the interval and final energy of the interval. So the only thing I need to identify is this, how to replace this number. So my one option is to look inside outcar, scroll it, which is quite boring. Scroll until I see a list of orbitals. And after I see a list of orbitals, I see, oh, okay, last orbital is 39. So it is number of bands. Okay? So I will replace this 1280 by 39. Another opportunity is to type grep NBA, and it is not National Basketball Association. It is, I'm just lazy to type n-bands completely. Grep NBA outcar, and it tells, see, number of bands 39. Okay, so now I'm opening it. Let me share this NBA stuff into your chat line. So VI Incar. So I'm navigating close to this number of n-bands and replace it to the one that I learned from outcar. Then I'm navigating further down and replace this numbers to, let's say, -8 and -2. So I want to cover the range of orbitals that includes HOMO and LUMO. WQ. And after I have this files, so it should be 4 standard files for WASP, POSCAR, PODCAR, K-points, Incar, plus the wave part or I would say W. After this, I can launch.
Dr. Killian,
Yes.
why did you change that to -8 and -2? The
What?
energy intervals.
Just a second. While we are speaking, I'll just launch it and let it go. So here, I want to plot to several orbitals, or I may want to plot it later. So I want to plot Homo orbital, LUMO orbital, and maybe a couple of orbitals nearby. So the code works in such way that it creates files for all orbitals in the interval that I select. So if I, right?
Yeah, I got it.
Okay. And while we were speaking, it has already created. So it reads the, it tells somewhere here. So the wave car file was read successfully. And then it tells the energy range from -8 to -2. And then it creates files for orbitals of these numbers. And let me bring the here. So if we are looking from -8 to -2, it will be orbitals from 23 to 39, right? You see their energies in the second column. So -7 something is bigger than -8. So, and then all orbitals here do belong to the range from -8 to -2. For example, for my exercise, I need probably only 32 and 33, Homo and LUMO. Now, and I will complete this demonstration and then make a walk through seats and ask you to try it. And you're welcome to try it as we speak. So after this job is complete, you see there are additional files which are called par charge. So I know you can be irritated either on your instructor or on the authors of the WASP software, but they use this strange language. So they call orbitals either bands or partial charge densities. But we should understand that those are just molecular orbitals or their analog for in this software. So if we would have the VMD software, one can download these files and immediately open them. So if you have VMD, you may try it, and it will be really nice pictures of high competitive quality ready for publication. If I do not have VMD installed here right now, there is a bypass. So I can, let me share you all know the command to run WASP. Since you completed homework, you have it. I don't need to share it. There is a set of tools that is free, and it was written by a team of enthusiasts, like community project, to process output files of WASP. And it is from the University of Texas, Austin, but one can download it free and put it on any cluster. So I placed them here in Photon in this VTS tools. So there are about over 100 commands. And right now we need the one charge to Q. So CHG to Q. If I just hit it, it will tell no, please mention the par charge file that you want to put. So I already did 32, maybe I should do 33, which is expected to be localized on titanium atoms. So I will do, and just a second, I'll copy paste the command. someone is typing problem using those commands. Let me finish for everyone, and then I'll visit everyone.
Okay.
Okay.
Yeah.
It may look long, but it is quite quick, or it is quick compared to other things that you have to do. So let me copy it right away to everyone. Copy. Go to chat. All right. Send to everyone. Paste. Yes. And after I launch this command, it will start arguing with me. It will tell like, which file format are you using? Total charge, local density, or not local potential, or par charge. And I will answer par charge number 3. By the way, we didn't start density functional theory yet, but you remember by analogy to Hartwig that one can speak about total mean free distribution of all electrons, which is basically charge density. And in the Fock equation, there is a kinetic and potential energy, how the electrons are attracted to ion minus adjustment for interaction with other elements, so potential. So this potential is also computed. And par charge is orbital. So we are telling that this file is orbital. I click 3. And then it gives me hard time once again. It tells enter element types by atomic number. I know that it is oxygen and titanium, but I will be plain open cards with you. I do not carry in my mind numbers of elements from periodic table. Maybe some of you who are professional chemists do, but yes?
When you entering the numbers into there, do they need to be in the order they are in the phosphor file?
Yeah, absolutely, yes. So let me fix my memory by looking into periodic table. So oxygen is number 8, titanium is number 22. So then I type 8 space 22. And then it reads per charge and creates a cube file. So it converts WASP style of output into Gaussian style of output. And then I can go into Gauss U, open, go to the right directory, select this file, open, and then in addition to just opening this file, I need to do the same stuff as I was doing in previously. So new surface. And now you see that it is primarily D orbitals localized on titanium with some admixture of a little bit on the oxygen. Make sense? So please try to follow this line and arrive to this picture. And I will visit probably first those in class because it will be quicker. And then I will visit everyone on online. Now we can wave to the camera down there. You will be very small.
Yeah, you can touch it.
Before COVID, this camera was operated really well. There was a remote control that was possible to focus on any seat and PTZ, panorama tilt zoom. But they reinstalled software and it stopped working. So, and I started just to bring a pocket camera with me. Okay. So, we can go whoever wants to go first, or just whoever is like I see first here is Sarah. Would you like to share your screen?
Yes.
Okay.
Professor, I just copy all the files that you need for this session, but I forgot how to what should be edit via by the VI command.
So let's do ls minus OT. Space minus OT. So, okay. You have wavecar, you have postcar, okay. Let's type more space Incar. Enter. So let's try type VI space Incar, uppercase. Enter. Arrow down, just by arrow. More down, down, down. Up, up, up. Stop at the end bands. Two more up. Now arrow right. Right, 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 right. Stop. Type letter I. Type backspace 4 times. Backspace. We delete. Backspace. Yeah.
Okay.
Stop, stop, stop. Now type 39. Now arrow down. Arrow down. Keep down, 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 down until second last, until the energy interval. Down, down, down. Down. Stop. Right, right, right. Delete, delete, delete. Now stop. Type -8 space -2. Now escape colon WQ. Now tilde slash bin bin slash wasp dash photon.
On the here the
Same as you were doing in homework. VASP. Just type VASP minus photon minus PH photon. Enter. So you see it creates band number 24, 25, 26. So it creates files for the orbitals. Okay, now type ls minus OT. Enter. So you see these par charge files.
yes.
Okay, now type tilde slash VT and then hit tabular VTS, just first 2 letters, VT, and it will continue. Yeah. Now type CHG number 2, CUBE, cube. And hit tab, it will continue. Yeah. Now type the name or copy paste the name of the orbital, of the file for the orbital that you want to draw.
Which one?
Oh, it's your choice. You can do something different, like maybe 34 or
Should I select this one?
yeah, select this one, paste, hit enter, 3, enter, 8 space 22, enter. Now type ls minus lt head, ls minus lt vertical line head. So you see this .cube file, right? So now, do you have Gauss view opened on your terminal?
Yes, I have.
Okay. And yeah, go to the main menu and open, select file type cube, file type. You are probably in the right directory, but file type, now it is GIF, but you need .cube. Yes. Open. Now let's go to results, surface contour, surface action. New surface. So this orbital is also localized on titanium, and it has D character.
Yeah, I see. Thank you.
Make sense?
Thank you.
Okay, you're done. You can stop sharing. Kea, would you like to share your screen?
This will stop other screen sharing. Desktop. Okay. Just a minute. So, Professor, this one. So all my file in LAB8. So
Yeah, that's fine. That's fine.
Yeah, but
so
I'm trying to copy Outcar, but then after that it shows something like that. I'm not able to copy. I don't know why. I already copy Incar, Webcar, Postcar, Podcar, Botcar.
okay.
K points, but Outcar, I don't know what happened.
I see. Do not panic. Everything goes okay. So type arrow up. Just arrow up. Space.
Space.
Period.
What?
Period. A dot, like at the end of the sentence. Period. Dot.
Like this? No, dot.
No, not colon, but one dot. One
dot, yes. Like this.
Enter. Enter.
Okay.
Now type ls minus lt.
Yeah, now it's work. Yeah.
So let's type grep space NBA N, uppercase N, B,
I think this one, right?
Yes.
Okay. Let's copy. And there. Oops. Why it's not work? No, it's not working.
Let's type, yeah, it's not so hard. NBA. National Basketball Association.
Yes.
Space Outcar.
Outcar. Enter.
Enter.
Yes.
So you see 39.
Yep.
Now let's do VI space Incar.
VI space Incar. Enter.
Enter. So arrow down. Arrow down, down, down. Until stop. Arrow, one arrow up. Now arrow left.
Need to change this number, right?
Yeah. Now type I, letter I.
I.
Or insert.
Now I am able to change the number, right?
Backspace to remove to erase old number.
What's the number? 6?
39 orbitals.
39. Okay. Only 39 in bands. Okay. Then
arrow down. Down, down, down until second last line. Down, down, down. Stop. Up. One arrow up.
Okay. There we need to
left. Erase. Do it. -8 space -2.
-8 -2. Professor, what is EINT?
Energy interval.
Okay, energy interval.
Now escape colon WQ.
Enter. Okay.
And now launch WASP by ~bin/.
Okay, that one. Just a minute. This, then bin, then.
I think it should be slash between.
Okay, slash. Yes. /bin/b.
WASP. Yeah, VASP.
ASP WASP.
Lowercase, not uppercase. Lowercase.
VASP WASP. Then
dash minus photon.
Minus photon. No space.
Not space. Like
minus photon. Enter.
So you see, it gives this all k points inside interval band number, and then it lists orbitals that it creates.
Inside interval band number.
Now type ls -ot, vertical line head.
-nt and.
So you see there are, or you can arrow up, or just type ls -ot. Yeah, remove head, and remove vertical line. Just
then enter.
Yeah, you see there are many new files starting from 28. So
this one.
Those are orbital files in WASP specific format.
Okay.
If you download them to your local computer, and if you have DMD software, you can immediately open them. But right now, let's practice it with Gauss view. So let's convert one of these files into cube format.
Then I need to copy this command.
Yes.
Let's try to copy.
I'm just giving you a heads up. I will ask you to do another homework where you will do orbitals of other models that you did in previous homework, and density of states that we will also cover today.
So here I need to write the charge.
3, yes, 3.
3.
Enter. 8 space 22. Enter. Now type ls -ot head.
ls -ot
vertical line head.
Enter.
Enter. And you see there is a cube file, right?
Yes. Now I need to open the Gauss view file, right?
Yes.
Excuse me, Professor. Before entering the atomic number 8 and 22, we inserted 3. What was that 3?
So it asks it asks for what was the file type? Was it charge, potential, or orbital?
Mm.
So if you read what it types to you, it is like a little obsolete type of interaction. In modern computers and cell phones, typically there are pop-up menu telling like click if you agree. And in 40, 50 years ago, it was just typing in the command line. They ask, if you agree, type 1. If you disagree, type 2. Something like that. So it was a little ancient type dialogue. Make
So
sense?
we insert 3 minutes for the orbitals, yes?
Yes, yes.
Thank you.
Professor, I have one question. So from this figure, you told before that this one D orbital. So from here, how could I understand that this one, which orbital shows there?
Thank you for the question. I do have the answer. I just process words in my head and mouth. So you have red spheres which correspond to oxygens, and you have white spheres that correspond to titanium.
Yeah.
So for this orbital, you have localization of this wave function or density of wave function around titanium atoms, right?
Hmm.
Now, if you please rotate it so it will look across the axis. So move it as we are meeting the arriving airplane. Just look into the front of the object so that minimal. Rotate, yeah. More so that we see only the front. That we see along the axis. Let me demonstrate. So you are showing this way, rotate it so that
Yes.
it has minimal vision. You understand?
Okay.
Minimal vision.
Now
Yes.
it's okay. Okay.
And align it even better so it's absolute alignment.
It's
Try,
correct.
no, try to rotate that it will be like minimal so that one atom blocks everything else. More, continue. More. Yeah, about this, yes.
Okay.
And now scroll the button on the mouse so that it arrives.
Zoom
Yes.
zoom in.
Okay,
Yeah.
enough. So now please stop sharing and or I will show something.
Okay. Stop share.
So titanium D orbital. See, here is the image.
Yes.
So D orbital has this shape of a flower with 4 petals.
Okay.
So by human analysis, the type of atomic orbitals contributing to these molecular orbitals look mostly like this shape, right? So one can make a judgment that highly likely it is a D orbital.
Okay. Now I understood.
Okay.
Okay.
So I think you did everything perfect. Now let me stop sharing and ask Lola, would you like to share screen?
Yeah, okay.
Yeah, thank you. Arrow up, arrow left, once.
Left. Okay.
Space. No, space. So, yeah, and hit enter. Okay. Do not worry, we will fix it. Arrow up once again. arrow left, slash, and type with uppercase Incar once again, same Incar minus dash and lowercase pc for partial charge. Enter.
Should I leave the period?
Huh?
There is a period at the end. Should I leave it like that?
Hit enter and we'll do something else. Now
Okay.
type arrow up, once arrow up. Now slash. No, space. No. Delete. Space. Period. Slash. Uppercase Incar. No, just arrow down. Yeah. Now type Incar. Enter. So you did copy the template, which is named Incar-PC under the name Incar. And this renaming is needed because WASP software is stupid. It is looking for the files named literally Incar. If it is something else, it will just ignore it. So we need to respect this stupidity of the program. Okay, now type ls. Enter. So you have in-car, out-car, wave-car, post-car, pod-car, K points. Now let's type grep space NBA space out-car. Enter. So you have n bands equals 39. Right? Now let's type VI space in car. Enter. Let's use arrows. Arrow down several times. Down until the now go back up until n bands.
Where?
N bands. So do you see where I'm fingering?
Okay. Yeah.
Now left. More left. Oh, sorry. I apologize. Right. I have forgotten what is left. What is right? More right. More right. Now type I for insert mode. Letter I. And go to the end of this. No. Keep being on this line. Stay on this line.
Okay.
Now arrow right. Right. And more. And now delete. Just erase to erase. Enough. Stop. Now type 39.
Okay.
So it was, you remember, it was the number that you put in the previous command. Now arrow down. Down. Almost to the end. Stop. Now go right. Delete. And type -8 space -2. -2. Now escape column WQ. Lowercase. Enter. Now just launch WASP, same as you did for the homework. Tilde / bin / wasp dash photo.
Sorry, say that again.
Just launch WASP. So tilde / bin / wasp dash photon. Enter. So it creates orbitals of those numbers. And now type ls minus LT. ls space minus LT. Enter. So you see these par charge files.
Yeah.
So let's convert them from VASP format into Gaussian, into cube format, and try to plot one of them. So you can either copy paste from the chat line, or I will spell the command. So tilde slash VT, and now type the tabular button so that it will continue tab, yeah, and now type CHG number 2 CUBE cube dot PL.
You say L or N?
Yeah. You can or you can hit tab it and it will automatically continue. PL. It's one of the languages. And now copy paste the name of the file that you want to convert.
Which of them is it?
Something like 32, 33, whatever. Right now we are just doing examples.
I can copy any one, right?
Yes, anyone. Okay, enter. 3, enter. Number 3. Enter. 8 space 22. Enter. And now ls minus LT, ls space minus LT.
Is there a difference if we had put the atomic number of titanium before oxygen?
Oh, you may. So let's scroll a little bit up. Scroll. Yeah, you see there is this par charge dot cube. So we will open it. And to make sure that we didn't make an error, can you please type more space postcard? More space postcard. Enter. Enter. So first is oxygen, second is titanium. We did right. So a comment for everyone: when you will be doing homeworks, these numbers like 8 and 22 will be different. For carbon and hydrogen, and then for silicon and hydrogen, different numbers. Okay, now
so we need to use more postcard to check the order, right? Is that what you're saying?
Please repeat. I was not focused.
I said that means we need to do this more postcards to know the order, because I was saying,
yes.
How do you know?
Yes, to check which elements you have. So now let's launch Gauss View on your computer if you haven't launched it yet. gview.exe.
It's launched. Nice.
It's launched. Then bring it up, or stop sharing and start sharing again by sharing the whole desktop. Okay, but we will need to see several windows. So here you click on the file open. File open. And now okay. File type. No, do not worry, do not panic. File type, and select .cube. It's about 5. Drop down. Yes, cube. Click, and now you see this per charge 12. Yeah, double click, and now you should go to results in the main menu. Results, surfaces, contours. Surface actions, surface actions, new surface. And I do not see, please bring up the window list. with model so that I see if you got it. If you're okay. Yep. Okay, very good, very good. Thank you. So it is hybridized basically between oxygens, and it doesn't look as symmetric because it is lower in the valence band on one hand, and another through optimization it was slightly changing the shape, so it's a little less symmetric, but it is okay. Yeah, thank you, Lola. I think you're good to go. You're done. And we didn't check with Lina. Lina, would you like to share the screen?
Yes. So this is orbitals, but I have a question, Doctor.
Excellent. Perfect.
Yeah, when I will just share the. Okay. So when I created the files for the orbitals, first I did create them for without changing the number of bands to 39. So first it gave me some other orbitals, but then I changed that so I could get some more orbitals like.
No, it's an error.
Yes.
Typically, if one types something wrong, it just rejects to work. But I think you convinced it to work.
Yeah, I'm wondering. I got similar results, but next time I have to change the number of orbitals, so it will be the right way. I think that's the only thing. But I have another question, Doctor. Depending on what we choose the orbital. So, for example,
please repeat once again. Just repeat last sentence.
Okay, so depending on what we choose the orbital number. So I choose, for example, 33. Lola chose, for example, 12. It gives different shape. So can you just explain to me what's the difference? Any explanation about the difference between these
two? Thank you for the question, and I do have the answer. I'm just trying to wrap minds in the words.
Yeah, thanks, Doctor.
Many electron wave function is a product of several single electron orbitals. The orbitals that are computed either by Hartree-Fock DFT, there are similarities between these theories, are occupied by Aufbau principles, same as in atoms. So there are several orbitals, and they are occupied by electrons. And it is just by how the nature is constructed. There are several eigenstates of electrons. Some of them have low energy that one can detect with LEED X-ray methods. Some are close to HOMO, can be probed by optical spectroscopy. So for chemistry and optical spectroscopy, only the orbitals close to the band gap are interesting and important. But for overall property of a molecular material, all orbitals are computed and used in the protocol, in the procedure. So in order to converge either Hartree-Fock or DFT calculations, all orbitals, including low energy ones, are computed. But for us, as materials scientists, low line energies with low orbitals with low energies are of secondary importance, because in most popular experimental techniques they are not probed. If the interest will be in spectroscopy, there will be not only HOMO and LUMO, but several orbitals below and above. And in case your system, your material, your molecule experiences, for example, charge transfer, if it is a material for photovoltaic, then there you will see examples where orbitals are localized on like left and right side of the molecule and show substantial qualitative difference. So when we'll come to projects, I will show you examples. But right now, one more comment. If you are studying some material with all depth and details, it could be reasonable to plot several orbitals, like 100 or at least 10, especially if it is your profession or your thesis, your paper. But if you are doing just quick educational approach and your time and resources are limited, just focus on HOMO and LUMO, because they are most of key importance. But if you need additional details, then look on other orbitals as well. Lina, does it address your curiosity, or you were asking about something else?
Yes, yes. Thank you.
Okay. Okay. Then you're good to go. Yeah. Thank you for stopping sharing. Now, in the remaining half an hour, we'll do the density of states. So you already know this concept. We were successfully doing it with Gaussian, and I'll make a demonstration how to do it in VASP, and then try to walk over the seats and try ask you to share screen. And if time allows, I'll do announcement about DMD and NERSC. If time doesn't allow, I don't know, maybe I'll share recordings from previous year or whatever. But density of states is critical. It is needed, and we cannot postpone it to other meetings. Share screen. Share. Okay. So I'm going to return to the original directory from the previous lab where I was doing the calculation. It is not critically necessary, but it is safer. So I'm going to the directory where the Incar was specifically tailored to find single point energy. And by the way, right now, I'm not going to do it, but if you change the number NSW to like 10, 100, or 1,000, the VASP will start optimizing geometry. I'm not encouraging you to do it right now because Photon is really our great friend and helper, but it is not as strong. When we move to NERSC, we will start doing optimization jobs and larger systems. But if you urgently want to practice something, you can relaunch VASP with number bigger than 0, and you'll see that it will change geometry, hopefully to the good. Okay, so here, outcar, successful outcar. If I do this outcar that corresponds to single point for geometry optimization at the end, I will, again, I'm scrolling. At the end, there will be, at the end, there will be a list of orbitals. So I do need a file that contains this list of orbitals, and I can do it in several ways. First, I can just copy, then type vi like list, I for insert, and then paste. So now I do have a list of orbitals, right? So it is one way, and I'm not it's not smart. There is another way which is also not super smart, but a little easier. So WC is not restro. It is word count. Word count outcar. So it is about 1,600 lines, and the orbitals are about after this declaration of energy Fermi. So if I type grep Fermi outcar, it will show the line that goes before orbitals, And if I type grep minus a, let's say 40, which means 40 lines after this record, it will show the list of orbitals plus something. Maybe I need a few more, 45. So let me copy to the command line. Copy. Chat. Please.
Professor, grep
Yes.
minus a 40, what's that means? That it means it will show the electron number 40?
No,
Sorry,
no.
44.
So grep is a standard Linux command. As all robots, it is silly and stupid. It knows nothing about electron or orbitals.
Okay.
So the grep command in this specific example means that we will inspect the outcar file. In this outcar file, we will find lines that contain word Fermi. So it is like in Microsoft Word, you can do like edit, find, and find specific word. And then it shows, it requests to show not only the line that contains this word, but also next 44 lines after this statement, right? So once again, if I look for the overall outcar, you see there is this keyword Fermi, then some other keywords, and then it goes to the list of orbitals. So instead of scrolling 1,600 orbitals, not orbitals, lines in this quite small system, and in the future we will have much bigger files, which are hard for humans to scroll. I am just looking for the beginning of the story and asking to tell the rest. And I already know number of bands, so I'll take number of bands plus whatever is here. So it is just a way, like if I would do your previous homework, instead of scrolling outcar, I would do this command. Now, same as in Gaussian, for making density of states, we need to save this list of orbitals into a specific file. So I'm directing it with this little caret into the file that I will call states. Copy, go into the chat line, paste. Now I can more states. No, it's not as good as I want. So let me maybe remove states and redo it.
More state.
No, do not do remove. So I probably corrupted something from previous commands. Now I look for more states.
More.
Oh, okay. So the word Fermi appears twice. Okay.
What happened?
No, nothing bad.
Okay. We don't need to do anything.
Nothing bad. What do you feel?
Ooh.
Okay, better. So let me share this command. And this has nothing to do with computational chemistry, just some tricks how one can process files. And one day one can write a script. And there will be available scripts when we move to NERSC. They are available there to do many good things in one line. So after this command, more states. The file states starts with something about eigenvalues, then the list of files, and then it ends. So for practicing the definition of density of states, which is summation of delta function, right? Centered at energy of each orbital, I need only data file. I need to remove any text, and I need to remove the empty orbital at the end. So I'm opening this states file, and I'm deleting dd. So it starts with 1, or I can delete more lines because I do not need this low line orbitals. If you find escape column, right quit. So now I do have a file named states with list of orbitals. I can also count number of lines, WC states. So it shows 39. So 1 line per orbital. Good. Now there is a little script that actually dresses each individual orbital with Gaussian profile. I know just from inside information that is something that Steven was practicing today in the morning. So bin dress those norm. So this script will look for the file named states, open it and process. And it will ask several silly questions. And before running this command, I need to prepare. Now I want just to demonstrate and then redo it. So it will ask number of states, which will be 39. And then it will ask this minimal energy, maximal energy, Fermi energy, alpha plus beta. Minimal can be -8, maximal can be -2. But for Fermi and alpha plus beta, I need to either scroll up here and copy paste these numbers. Fermi and alpha plus beta, this one. Enter. But I better prepare. So I do once again grep. And I also need to learn number of ions in the model. Here for small model we know that it is 12, 8 plus 4, and number of electrons. Number of electrons. Let me copy this little commands. It will make your life easier, I hope. Paste number of Fermi. Copy. Paste and correct number of electrons. Copy. Paste. Okay. And now I'm ready to answer these questions and WC states. Now I'm ready to run this dress dose norm. So number of states 39, minimal energy -8, maximal energy -2, and Fermi energy -6.8749, and then alpha plus beta. Its correction because of we have alpha and beta electrons -1.2572. Enter width of each line, for example 0, 1. So the idea of density of states is converting discrete set of orbital energies into continuous distribution. And for contribution from each individual line, we need to assign artificial width. And one can take it something related to the quantum of thermal quantum. or here we are not doing literal science. One can also select something artistically that would give sufficient broadening to length, not too broad, not too thin. Let me finish. And it's interesting discussion. And so magnitude 1, number of atoms in the simulation cell. So number of ions is 12. Number of electrons was 64. These numbers are needed for normalization. Gap of the bulk phase of the same material. It doesn't change anything in this calculation. Just a second. Let me finish, and then I'll ask questions. So for titanium dioxide, in the Wikipedia, you can find 3.2, and then it tells DOS Fermi file is written. So I'm going to answer questions, and just in case, let me copy the whole this whole dialogue as a. Sorry for like not answering immediately to several questions. And if I type ls minus lt here, I do have new file which is called DOS Fermi. Okay, so before we go forward, I heard a question from Boston first and from Kea second. So Boston, what was your question?
Oh, I just thought that the width of each line. So I was trying to understand that. Is that kind of like a bin size? Or like
No. I'm going to erase this plan, right? And you are thinking in the right direction, but it is if you would have like thousands and millions of orbitals, like really dense, then we can create an interval from E to E plus delta E and count how many states are in this interval. And the higher the number, the higher the heights. So it is what Boston is asking. So bin size. In size, like basket where all orbitals are coming. We are doing differently. The result will be the same in some limits, but we are taking individual line and assigning it to read. Then another line and assigning it another read. And then we add together. So if the lines are resolved, it will be such figure. But if the lines are close enough, then it will be just a line that is thicker and taller than individual one. So in the limit of infinite number of orbitals, the density of state, the shape of the density of state will be independent of this parameter. So it's kind of more artistic tool rather than scientific method. So you have freedom to choose it, but it is reasonable to start playing near the value of room temperature quantum, which is about 0.027. Okay. Kea, you had next question?
Yeah, Professor, when you showed some command, so you did you delete something? Like when I write WC states, it shows 44 atoms, like number of 44 states. Number of states is 44.
Number of lines.
Number of lines. Yes.
Number of lines and number of lines in the file and number of orbitals in the file states are different. So let me repeat this command that I was doing. So I'm going up. So I did this command. You see it, right?
No, I'm not able to see anything because camera.
But not camera. I'm sharing screen.
Okay, sharing screen.
Yeah, I believe I'm sharing screen.
Okay.
But okay. So here I focus camera on it as well. So this command,
Hmm.
after I hit it, do not repeat after me. I
Okay.
believe you are already ahead of me in this.
Okay.
Now, if I do WC of the states, it has 44 lines. And if I look inside
Yes.
this file states, it starts with text, which I do not need. I need only numerical file. So
Yeah.
any text must be deleted. Therefore, I'm opening this file in VI,
Okay.
go into the first line, and typing letter D. Delete,
Hmm.
delete, delete, delete. And after that, I'm typing escape column WQ.
Okay. That now I
Or-
understand.
Okay. And also there is a empty line at the end, which I also do not need. So I open the file, go into the end, and typing DD once again, DD. So there will be no empty line at the end. Now I type WC states, and it will be number of lines in the file is equivalent to the number of orbitals in the calculation.
Okay.
Okay, so ls minus LT. After I finished the dress DOS command, I
Mhm.
got this DOS Fermi. So DOS Fermi is a continuous many points corresponding to density of states. And I will finish demonstration and then start visiting.
Okay.
So GNU prod tilde bin GNU prog. And there are also, you see, there are several templates. So I do GNU prog underscore DOS. And I'll probably try just GNU prog DOS without anything. But later on, I may try. And now I'm typing ls. No, let me copy paste it into the chat line. P chat line. Paste. Then I'm looking other any new files, and I see there is a file dos.ps, right? And which I can convert by ps to pdf wr dos.ps. So it creates dos.pdf. So which I'm going to download and check if it is helpful. Copy, chat, paste. So of course it will be useful skill for me to transfer files by command line with copy, but let me just quickly use this Windows style, so Scratch 001, chem676, chem676 year 25, density dos.pdf. Okay, so here is, I think it did work okay. And so now please try to reproduce this figure to best of your ability, and I will visit first those who are physically in the class, and then I'll ask you to share screens. Now we are again on the back camera. Okay, so I'm back to this little camera. Stop sharing. And Sarah, would you like to share your screen?
Yes. Yeah, I am entering the energy.
Okay, just keep typing this -6.87 and hit 87 and hit enter. You do not need all digits. Yeah, enter. Then -1.25. .01. Enter. 1, magnitude 1. Number of atoms 12. Enter. Number of electrons 64. Enter. 3.2. Enter. LS minus OT. So you have dose Fermi. Now type GNU plot. Remove 1. I think 1 is not needed. Enter. LS minus OT. Now, so you see dos.ps. Now type ps to PDF. Yeah, enter. LS minus OT. You see this file is here. And now, on this panel, double click.
Okay.
Yes, perfect. You're done. Yeah, thank you. You can stop sharing. Lola, would you like to share screen? The LS minus OT. You don't have the states file.
No, I haven't even. I'm still like way behind because I couldn't.
Oh, do not worry. We will pick it up
Okay.
momentarily. Type grep space Fermi space outcar. Enter. Now arrow up, arrow left. More. Yeah. Left. Few more before Fermi.
Okay.
Space minus capital A space 44. Enter. You see, it gives you lists of orbitals. Now arrow up.
I thought you said it's supposed to give me the ones after 44. I don't know. I'm kind of like lost.
Where the number 44 comes from? We already know there are 39 orbitals. Plus, there are some additional lines between the word Fermi and the table of orbitals. So therefore, I add 5 lines. I suggest to add more lines. So now let's do vertical line.
So is it like 44 is like a good number, or how do you know the
number of orbitals plus 5?
Oh, okay. Sorry, what did you say?
Please type vertical line.
Vertical line where, sorry?
Vertical line.
After outcar?
Yes.
Sorry, to look for it.
Okay. Oh, yeah, it is here. Good. Now, after vertical line, type tail. Tail space minus n lowercase minus n space 40 space bigger, the angular bracket bigger. Let me show. No, not smaller, but bigger. Opposite. Yes, bigger. The one after, yeah, the one after the question mark. Yeah, bigger space, and now uppercase states. States with uppercase states. Enter. Now type more space states. More space states. Enter. So beginning of the file is really great. Now hit space a couple of times. So the only shortcoming that there is an empty line at the end. So we need to delete this empty line. Type vi space states, lowercase vi space states, enter. Now arrow down to the very last line. Very last, very. Now type D. And now escape column WQ. Enter. So with this DD command, you erase the empty line at the end. Now type WC space states. not states. Enter.
Sorry, what's WC again?
Word count.
What count? Okay.
So now we have agreement. There are 39 orbitals and 39 lines in the file. Good. Now let's type once again.
Other numbers.
Let's get some other numbers that we will need for density of states. Let's type grep Fermi outcar that you already did before. Grep space Fermi space outcar. Enter. Now let's type grep space NIO with uppercase NIO. Number of ions space outcar. Enter. So number of ions 12. You see at the end. Now let's type grep space N uppercase NELE. Not M but N for number of electrons. Number of electrons. NEL space outcar. Enter. So 64 electrons. And now we can start with generating density of states. So tilde slash bin slash dress uppercase DRESS underscore DOS with uppercase underscore NORM 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 norm. First letter NORM. Enter. Number of states 39. Enter. Minimal energy -8. Enter. Maximal energy -2. Enter. Fermi energy, whatever you see here in this -4.55. You see it in, yes, exactly. Enter. Alpha plus beta, the one that in the same line, -1.43, yes. Enter. Width of each line, just repeat this number, 0.01. Enter. Magnitude, 1. Enter. Number of atoms in the simulation cell, 12. Enter.
The number of ions.
Yes, number of ions, correct.
Okay.
Number of electrons, 64. Enter. Gap of bulk phase, 3.2.
Where did you get 3.2 from?
You can find it in Wikipedia, but I assure you that this number doesn't change anything. It was from previous version of the code, but enter. So DOS Fermi file is written. Now type ls-lt. Enter. So you see there is DOS Fermi. Now we need to create the DOS.ps. So please type GNU plot space tilde slash bin slash GNU prog GNU prog underscore delete letter P, GNU prog without P, GNU prog, yeah. GNU prog, like program for the program. GNU prog, letter P shouldn't be here. Yeah, underscore DOS, D uppercase DOS. Enter. ls-lt. Enter. So you see DOS.ps.
Yeah.
Yes. And now let's convert it into the PDF. So PS is lowercase PS, 2, number 2, PDF WR space DOS uppercase dot PS. Enter. ls minus OT. So there is a dos.pdf. Now, yeah, let's find, yeah, reconnect browser. Yeah, scroll up, green, scratch 001. Yeah, this one. And DOS, the red one, dos.pdf. Yes, double click. Did you double click it?
Yes, I did.
Is it downloading?
Yeah, it's coming up.
Okay, perfect. And you see, there are some little changes. The gap is slightly smaller and profile is different because the angles between elements in this nanowire were twisted. But overall, qualitative result is the same. Excellent, excellent. Thank you. You're done. You can stop sharing.
Thank you.
And Kea,
Yes.
would you like?
Just a minute. Professor, up to this, before this command, it's okay.
Okay, now type arrow up.
Just a minute. I need to go down.
Yeah. Arrow up. Enter.
Command not found.
Oh. Okay, not
okay.
gun, but no.
Okay, now I understand. Ish.
We are not mafia with guns, like.
Oh, now I understand why. What's the mistake? Gun.
Okay.
Now it works. Then
ls minus LT.
Now it's okay. Then I need to type PS, then 2 PDF WR.
Correct.
DOS dot PS gun.
Okay, ls minus LT.
ls minus LT. So we already have. So which one need to go? The previous one, this one.
Yes.
I think. Let's see. Yep.
Perfect. I think you're done. You can excellent. Stop sharing.
Okay.
And we do have Lina. Lina, would you like to share a screen?
Yes, sure.
Thank you. Is this photograph in San Diego?
Yes.
It looks like convention center.
Yeah, exactly.
American Chemical Society conference.
Yeah, it was a Biophysical Society.
Okay.
I will share. What is that? Okay. Sorry. So I already followed.
Perfect.
Okay.
Okay. So I think everyone did. Thank you. Everyone did really great. If you have some plans for the evening, feel free to disconnect and depart. I'll just give some quick quick comments. If you want, you can stay and watch. So Google type VMD, Visual Molecular Dynamics. So if you click on it, there you can start to explore this software. There will be the software VMD download. So you can select whatever is your file, but it will ask username and password. So do not worry, it will not pull money from you. They only want to count how many people across the world are using their software. So if you click on continue for registration, well, I will not do it on the fly, but if you explore this web page, there will be so one of these buttons here on this page will allow you to register. You just give your email in academic institution, and they will send you a password, and then you will type this username and password, and they will let you to download. If you want, I can show now or next time I just share recordings how it works on other computer. I have it installed on the laptop, and it creates, on my personal taste, much higher quality than Gauss-Lee. On one hand, on another hand, VMD software does recognize all details of VASP, not only orbitals. Specifically, when one computes molecular dynamics, when positions of ions are changing, VMD naturally allows to convert the output of VASP into movies. So if you are recording chemical reactions, evaporation, condensation, molecular beam falling onto the surface, so anything with dynamics, it is the best software for such processes. And we will cover molecular dynamics in 3 weeks from now, 2 weeks after start of after the break. And molecular dynamics will be key part of the project. So I strongly recommend you to export. Let me copy paste. You can find it based on these 3 letters, DMD, but just in case I copy to the chat line. Paste. And another thing that I want to start right now. So I'm going to share something that I'm asking you, please do not overuse before you know. I will open your door to like strong facility, but where is the? I'll stop the recording and tell something. Pause sharing. No, not pause sharing. Pause. Resume recording. So you got basic idea, and when we meet again, we will develop on it to give additional options to use supercomputer facilities. So for homework that, and I shouldn't give you too hard work, so you will get angry and disclose this thing. But for the next homework, I will I'll announce it on Friday. But for the break week, I will ask you to practice density of states and homo-LUMO orbitals of another 2 models that you just reported, ionization and affinity, right? And after you do that, next time we meet, we'll go to optical absorption, spin up, spin down, and molecular dynamics. So with this, the lab is done. Many thanks for investing your precious time and staying over hours or limits. Anyone is welcome to disconnect or depart, and I'll stay here just to ask if there are any additional questions.
Thanks, Dr. Kellan.
Yeah, thank you.
Night, everyone. Bye.
Good night.
Good night.
Thank you. Goodbye.
Thank you. Goodbye. See you on Friday.
Professor, I have a question. You wrote something when I submit my assignment that, let me read your email. There is a little detail which can be improved, but please.
Oh, okay. So,
so
but
which
let
one?
me check if there are questions from Boston and Steven.
I've got a few, so you can handle her first.
Huh?
I have an unrelated question. I'm using that.
Okay, is it a question or a comment?
Question, but it's not related.
Okay. So I'll probably answer at least the first question of K and then go with you. And then
Yeah.
if you have more questions, I'll just rotate and
Okay.
cite.
Yeah, it's
So,
okay. Everyone can see this one. Okay. So this one, like you sent me these
yes. Okay.
things like
Let me go to your directory.
homework.
Uh-huh.
Okay, my directory. Yeah. Homework 7. Yeah. Homework 7. Yes.
Right here. Right. This
yes.
one?
Just a minute, Professor. Which one? You will need to
I am
show.
in the directory.
Yes. Yeah. So first one. So if you want to open the log file, then that means
I see things. So
okay.
let me do make directory optimization. Copy concar as file, and also I want to copy the key points in car. What car? I also can copy wave car, it is available, but it is not so necessary. And now I'm going to this directory of optimization, and I'm looking on this Incar, just in case reducing this parameter and typing here. Right now I will type 10, but for more of optimization, one should use bigger numbers.
Okay.
10, exit, and type in wasp.
Photon.
So you see, this is one electronic iteration. This is next electronic iteration, and inside there are several ionic iterations.
Yes.
So you see, it repeats again and again and again. So it will do it. Now we are on step 5. Now step 6.
It will show up to 10.
7.
Because
it will stop as it reaches 10. And I'm just giving an example.
Yes.
So 9, and now will be the last one, 10. Writing wave functions. Now I'm doing so I did this XDAT to XYZ, and now let me do Gmo. Steven and Boston, I will be done momentarily.
So it's another way to fix the atomic model, right?
It's just I'm demonstrating optimization in VASP.
Okay.
So by changing the NSW parameter.
Okay.
So here is your model, right?
Yes. Yeah.
And I'm going extra animate. So you see it breaks on pieces, which is not good. Maybe something was not ideal there. So if it breaks in pieces.
Why it's breaks into pieces, Professor? What happened?
I don't know. Maybe the boundary conditions were not correct.
Okay.
If I would redo this model, I would put. Let me atom labels, atom numbers. So this hydrogen number 8 should be arranged same as hydrogen number 5, upwards.
Okay.
So it is. I hoped that through optimization only this hydrogen will move, but maybe the whole model should be redone. And so please try it. Right? Try to redo the model by or just move this hydrogen number 8 upwards.
Okay.
And I'm going to close this one. Another thing, VIK points. There is a trick if one uses at least one K point in the direction of growth of the model, it may stabilize the model substantially. So some decomposition may happen because we didn't use K points.
Okay.
So just do not worry. Nothing will affect your grade. It is only little experiments, but you may, if you have time and wish, please practice it. And
sure.
Send more emails to me. So, okay, I want to speak to Steven in Boston because it looks like they are on schedule to move somewhere. But
okay, so you already answered the question. No, it's fine. Professor, that's the thing. I told you that I will send you the video for the second presentation. It will take time. At the end of the break or during the this break, I will make that video because it's time consuming. That's why. Okay, Professor.
Okay. Yeah. Thank you, Kia.
Okay, Professor. See you on Friday.
See you on Friday. Yes.
Bye.
Bye. What's that?
Something I was wanting to simulate earlier was how 2 layers of 2 different atoms.
Okay.
How would I model them melting and becoming an alloy?
Just practice molecular heating and molecular dynamics, same as you already attended earlier, and we will cover in 3 weeks from now. So, you can select project for this class, whatever is interesting to you. I see this ruthenium trichloride as most promising, but maybe you see something else, maybe something related to your actual research. Maybe you can do this fun stuff, this melting.
So that came up because a few weeks ago, the university put out offers for grad students to make videos to show to high school students. The experiment that I wanted to do is called golden pennies.
Yeah, I remember.
So pennies are covered in copper, which you then plate them with zinc, and heat it over a flame, it will melt, it will become brass, golden color. So I was like, well, I should probably put in a photograph representation because that's what I think the model of an alloy.
Yeah, it's very, very appropriate. And it is the kind of problems for which VASP software was originally designed.
I'm going to
go.
Would you like me to leave pizza in the lab?
No, I will not visit the lab right now. I'll go directly home. But thank you much for offering this. Much appreciated.
So another question first is
Once I need to put something here. Just trying to feel like, if your computer is relatively good, its space will substantially double. I'll stop recording because probably getting things away from the person. It is not as